Hi, everyone. My name is Shreya. I'm a software engineer at BuzzFeed, and I'm on the security infrastructure team. Our team is responsible for creating tools for developers to make software that follows the best security practices out there. I'll be talking about a specific tool called SSO. We recently open sourced it. It's our homegrown solution to securing microservices on Amazon Elastic Container Service. Okay. So this is a little bit of an overview of what I'll be going through in this talk. I'm going to start off with some background into BuzzFeed's tech, org, and infrastructure, and go over why we felt it was necessary to build our own solution to securing microservices. Then I'll go into detail on what SSO looks like. And lastly, I'll talk about our experiences open sourcing SSO and discuss why and how we went about doing that. So before I go into detail about why we built SSO, I think it's necessary to give some background into what BuzzFeed is as a company and our tech organization. So BuzzFeed is an independent digital media company. We create content that spans a wide range of media with the goal of delivering news and entertainment across the globe. We strive to give people content worth sharing, like our award-winning investigative journalism, tasty videos to make during the holidays, or like the best big new viral cat video. Our tech team is responsible for creating content, for ensuring that this content is reliably accessible and discoverable across a wide variety of platforms, from Facebook to YouTube to our own BuzzFeed platform. Our tech team also creates tools to make content creation as easy as possible for our producers and our writers. As our organization grew into what it is today, our tech team recognized the ability to work fast and build infrastructure that would scale as the tech organization grew. We focused mainly on consistency in our infrastructure. We believe that this would facilitate developer best practices, and it would allow for flexible mobility across the organization to work on the things that were most important to work on. One decision that helped us establish these goals was to have a monolithic repository, or a monorepo. A monorepo contains all of the source code for all of the services that run on BuzzFeed's infrastructure. Using a monorepo simplifies service creation by removing the need to create additional repositories. Cross-C mobility is simple, and we have a unified workflow. One particular workflow is our deployment workflow, which is facilitated by an in-house platform called RIG. So RIG is a platform made for deploying and testing services. It leverages containerization, and it's built on Docker and Amazon ECS. It uses Amazon Elastic load balancers to maintain traffic to the services. RIG revolutionized developer productivity by standardizing the deployment workflow, from validating and testing services locally to deploying them into staged and production environments, and bringing that whole entire power in to execute that process into the hands of the developers creating those services. RIG was introduced into our tech ecosystem a few years ago, and since then, our tech organization has grown significantly, and the amount of microservices that we maintain has as well. We have around 600 microservices in our monorepo that are deployed with RIG, and these services can be broken down into a few different kinds. We have 250 UI services. These are internal tools that have a UI and need to be exposed by the internet. 150 API services, and 150 message queue reader services that are used for publishing and consuming messages. I'd like to focus on our UI services for this talk, which were mostly internal tools that are responsible for helping editorial make posts, video producers publish and edit videos, and developer tools for deploying, monitoring, and testing services. And we recognized that there was a necessity to secure these services. So how do we secure our services? Securing services is not a novel thing, and there are many solutions out there. So when initially approaching this, we considered our options. We came up with some criteria surrounding what we wanted in an auth system, and when thinking about this criteria, we decided that consistency and positive developer experience were the two most important things to consider. So we wanted setting up authentication to be consistent across all services, as this would make the developer experience for adding auth to new service a simple, known process. We wanted the service to be accessible to the public internet so that it was simple as possible for anyone in the organization to be able to use the tools that they needed to as easily as possible. We wanted to have granular access control, ideally on a per user, per service basis. And lastly, we wanted setup to be as simple as possible for both the developers writing these services and the users accessing them. With this criteria in mind, we considered a few options. The first two were using a VPN or leaving creating authentication to be something that was baked into the services themselves by the service owners. And these options only both partially fit our criteria. A VPN does have consistency, but it also is a binary access model. So you can either be inside the corporate network or outside of it. And it did not have access control baked into it. And I'm sure many of us know how annoying it is to connect to a VPN, let alone figure out how to set up the infrastructure for one. Another option was to punt on coming up with a way to secure our services altogether and allow our service owners to bake that into their service applications. However, this inconsistency was something that we did not want. From a security observability perspective, we would have none into how secure our services were. We wouldn't have any access control defined either, and service owners would need to refigure out how to add authentication, which would not be an ideal setup experience for developers. And so, saving best for last, we had an ideal third solution, something called an identity-aware proxy. The concept of an identity-aware proxy comes from a white paper from Google defining its Beyond Corp philosophy. The center idea of this philosophy is to shift authentication access control to be something that is based on the user's identity rather than what network the user is in. An identity-aware proxy is a service that sits between the user and the service and uses a third-party auth provider like Google to authenticate and authorize the user trying to log into the service. There would be consistency as every service would be using an identity-aware proxy. It would be accessible from the public internet. Access control would be based on the user. And there would be simple setup for both the developer and there would be no setup for the user. So this method of securing services satisfied the criteria we had and came in the form of an open source Go application from Bitly called oauth2 Proxy. Every user-facing service would have an auth proxy service that accompanied it that would run the oauth2 proxy binary. So Packland would have a Packland auth proxy service that sat in front of it. And this was fine in the beginning when we had a few services before we had 250 UI services. But as developers made more internal tools, we recognized that this solution did not scale. These scaling problems were felt all around. By developers who created the services, by the infra engineers who maintained the oauth2 proxy services, and by the users accessing the services. So to start, in order to create a new user-facing application, developers would need to copy boilerplate oauth2 proxy configurations into a new service. And to most of the developers, what these configurations meant was completely opaque to them and confusing. Maintaining these services left a lot to be desired as well. In one case, we found a critical security bug in oauth2 proxy, and we needed to apply this fix to all of the services. And this meant ensuring that the changes were made in every single service. And this was not only tedious for the engineers maintaining the oauth2 proxy services, it also created a large surface area for the potential of an attack. Users accessing the services protected by oauth2 proxy also had an unpleasant user experience when logging into multiple services. Since each oauth2 proxy service was a standalone authentication flow, it meant that a user would have to sign in with Google each time they accessed a new service secured by oauth2 proxy. This also promoted bad security practices as people would blindly click through these prompts and not verify that they were using their credentials to give permissions to the appropriate services. So after recognizing that these scaling issues were a problem, we realized that we needed to rethink the way that we secured our services. And we knew that we didn't want to reinvent the wheel and decided to use the logic of oauth2 proxy to create SSO, a single sign-on version of oauth2 proxy. One thing to note is this was 2 years ago, and we did look for other alternatives, but nothing like this really existed back then. So I'm going to go over what SSO is now. One of our engineers came up with an RFC for what is now SSO, a nested OAuth flow that creates a single sign-on experience. SSO is an implementation of an established standard protocol called the CAS Protocol. It stands for a Centralized Authentication Service, which consists of a CAS server, or a centralized authentication server, which is responsible for authenticating users and granting access to the services, and a CAS client, which protects the service and uses the CAS server to retrieve the identity of the user. SSO has these two parts, where SSO auth is the CAS server and SSO proxy is the CAS client. And this is what SSO looks like today. It's composed of two separate Go binaries and a third-party OAuth provider. The upstreams sit behind SSO proxy, and SSO proxy reverse proxies the requests after authentication and authorization have occurred. I'm going to go into a little bit more detail about the different components of the system. SSO proxy acts as an identity-aware proxy for the services sitting between the upstream and the user. It stores a short-lived cookie session that refreshes every minute or so with SSO auth, and the refresh with SSO auth is done behind the scenes, so the user doesn't see any of this. SSO auth, the other part of the system, acts as the authentication provider for SSO proxy, and it uses a third-party provider like Google to authenticate the user and stores the user identity information in a long-lived cookie session that lasts around 15 days. And when this session cookie expires, a user is redirected to a sign-on page. We use Google as our third-party OAuth provider, but we are working with the open source community to support other providers like GitHub or Azure or even Amazon Cognito. And then lastly, the upstreams, or the services that sit behind SSO, sit behind SSO proxy. They are defined in a YAML config file because, well, everyone uses YAML and we wanted to too. Service owners can set the address mapping of the internal service to SSO proxy's address and add options that allow for group-based authorization or request timeouts. Also, service owners can set up vanity domains that point to SSO and create overrides for certain clusters like prod for a better user experience. So instead of having to go to pacland.sso.prod.pacworld.io, a user would only have to go to pacland.com. And so those are all the components of SSO that work together to create our nested OAuth flow. Here is a flowchart of the authentication logic of SSO, which either ends up with an error page if the user is not authenticated, or directs to checking that the user is also authorized. A user is by default authorized for an upstream, but in the upstream config file, they can set up access control via Google Groups. So to show the new user experience for a user logging into SSO, I'm going to go through a quick example that's actually found in our quick start guide in the open source GitHub repo. So we have two services in this upstream config file, HTTP bin and a Hello World app. And as you can see, one of these services, HTTP bin, is restricted to only the users who are in the admins at pacworld.io Google group. So I started up these services using Docker Compose, which can be found in the quick start documentation in the open source repo. And first, I go to HTTP bin behind SSO, and I'm directed to log in with my Google credentials. After logging in and entering my 2FA, I get directed to the HTTP bin upstream. Then when I go to Hello World behind SSO, I don't get prompted to log in, and I automatically get directed to that upstream. If I were fired right now, and by the time I finish this presentation, I would not have access to any of my services, as SSO proxy refreshes with SSO auth every minute. So that's a little bit about the architecture of SSO. After 12 months of running this in production, we decided to open source the project for a few different reasons. First, SSO was born out of an open source project, Bitly's OAuth 2 proxy. So it naturally made sense to give back to the open source community. When talking to other organizations who had similar problems, they were interested in a solution like this. Furthermore, we believed that granting access to our code base would force us to improve our security practices. We know that security is very difficult to get right, and open sourcing this project forced us to better understand what our security footprint was. We also believe that open sourcing a major security project like SSO would raise BuzzFeed's profile in the open source world and could draw in promising talent. But this decision was not taken lightly. There are not many open source security tools out there because it's scary to open source security. When thinking about how we were going to execute this open source, we made sure to consider what makes an open source project successful and what we could do to mitigate the risks surrounding open sourcing a significant piece of our security infrastructure. And so this was the list. This is like a little bit of an overview of what we came up with. To start, we made sure that we had substantial documentation to make getting started with SSO as easy as possible. We focused a lot of our efforts on a quick start guide to lessen the barrier of entry for using this project. We think that having this quick start guide was a major part in its success for getting people to start contributing and using SSO. Another thing that we decided was important was to change the name of our project, actually. The original name was COP, for Centralized OAuth Proxy, and we didn't think this was a suitable name. And there were two reasons for this. First, we wanted to step away from this acronym because we wanted the name of the project to be something that was inclusive of all communities that might want to use this open source tool. We also thought that for the future of this project, rebranding would allow us to expand the project past OAuth. So I started by polling our engineering team on naming suggestions, and we got some really interesting ones. I'm sure a lot of you understand how hard it is to come up with a product name. We also considered names like Elastic OAuth Proxy, but we thought that was a little too close, and Amazon might talk to us about that one. And so we ended up coming up with something that was simple and self-defining, SSO. So in addition to these refactoring and documentation changes, when beginning the open source process, we had larger conversations around what risks we were taking by open sourcing SSO and what we could do to mitigate these risks. And we decided to take a three-pronged approach to auditing our security, the security of our project. We were already using a bug bounty program called HackerOne for a bunch of projects within BuzzFeed, and since the start of having SSO in production, we used the same bug bounty program. It allowed us to pay for security vulnerabilities found by security experts. Before open sourcing, we contacted a few known hackers and gave them access to the code base to see if they could find any vulnerabilities by having the ability to pen test along with having access to the code. We also hired a third-party company to pen test SSO and provide code review. And we interviewed a few companies, decided on one, gave them access for a 1-week review, and nothing significant really came up, but we were happy that we had the peace of mind of getting this review done. Lastly, we have an in-house security consultant who did an architectural review of SSO with the code and actually found something really interesting surrounding the way that we encrypt our session state in our cookies. So our session state contains user identity information, such as emails and the refresh and access tokens that we get from Google. We encrypt this state using AES, which is called Advanced Encryption Standard. That's what it stands for. And we store these encrypted values in session cookies. And we do this in part because we want to negate the necessity for any sort of persistent data store in SSO at all. So using AES requires having a nonce, or a number that is used once. And since we don't have any type of persistent data store, we create our nonce by generating a random number, which also means that we cannot guarantee that our nonce will not be reused later on. We originally used a cipher method called AES GCM to encrypt our values, which is encryption based on a counter, which turns out is susceptible to an attack called a nonce reuse misuse attack. and it's something that happens if a nonce is used multiple times. And this attack can ultimately lead to the potential of exposing our session state value in plain text, which is not good. Our security consultant pointed us to a different type of implementation and a package. The package was called Miscreant. The implementation is called AES Civ. And this is resistant to this kind of attack and only provides the same ciphertext if the same nonce is used twice. So in addition to fixing this potential vulnerability, having this resource also allowed us to learn about a different type of encryption method and further our team's understanding of security best practices. So after going through this security audit process, we felt more prepared. But beyond preparedness, understanding that security is never completely done was crucial. Our team has a learning and growth mindset about all of our work, and this includes acknowledging that unknown unknowns do exist and that we will have to continuously adapt. Nothing is ever 100% guaranteed to be secure, but careful planning and good communication and clear expectations allowed us to assuage our initial fears. So then we finally open sourced SSO, which is an exciting day. Since open sourcing, we've had some great contributions from the external community and have worked actively on engaging with this community. So that's a little bit about our security infrastructure at BuzzFeed and SSO, a tool that has been a game changer in the way that we secure our microservices on Amazon ECS. Thank you for listening, and please feel free to check out the open source repo. We would love to get any feedback as issues or pull requests, and would love to have you as part of our community. Thanks.
Oh, thank you. Now I guess we're going to turn to Slido. If you have any questions, head to slido.com, #startup. You can type them in there, upvote other people's questions that you want answered, and we'll work from there. So to start, can you talk more about the responsibility of the apps for authorization?
Talk more about the responsibility
of the apps for authorization.
Oh, sure. So we leave all of the authorization part of it to be defined in an upstream config file that is defined via Google Groups, and we strongly encourage our developers to have that kind of authorization. Most of our services have a general engineering at our organization as a baseline of our Google Groups who are authorized to access our upstream. Yeah.
Awesome. So how do you handle SSO for Lambda functions and serverless if you guys deal with that?
We currently don't internally handle it for Lambda functions and serverless. We have a lot of people in the open source community who are actually contributing and trying to make it more usable for these use cases. Yeah.
And then did you integrate any MFA with your services?
We have MFA with our Google email account. We don't have any MFA integrated in SSO because it's a proxy that I guess we didn't see a necessity for that since we already had it in our infrastructure. Yeah.
Cool. Any more questions? She'll also be around after the talks if you want to ask in person. Totally feel free, but let's give her a hand.